Okay, so the diffraction grating shows the same diffraction pattern as a double slit apparatus. So everything's the same as with the double slit, except instead of the way that we define what D is. D is the distance between the slits on our diffraction grating, but there are lots of slits. There are hundreds or thousands of slits on a diffraction grating. The mathematical description is also the same because the geometry works out exactly the same. Is that D sine theta is equal to m lambda, where m is equal to 0, 1, 2, 3, and on and on. And these give the positions of the bright spots. So exactly the same as a two-slit diffraction pattern. These are the bright spots. Let's see, I think you have a little practice question here you can do on your own. Here I want to know how many bright spots are on the screen. I'm going to help you out with this just a little bit because I want you to think about this. If I have this diffraction grating, you know, I'm going to draw it as a double slit, but well, let's see, I'll come back and I'll draw it as a diffraction grating because this is physically what you have. You have this a whole bunch of slits like that. They would be really close together. In fact, the distance between the total distance between the slits is very, very small. So I have my distance L. This is my angle theta. And I want to know now how many bright spots are on the screen. Okay, so I'm looking at this expression, d sine theta equals m lambda. And I want to know, what is the limit for this? Like, how many bright spots can I get? Physically, I'm limited by this angle theta, because once this angle theta exceeds a certain value, the light doesn't go on the screen, and that value is 90 degrees. So when theta is bigger than 90 degrees, or when it goes up to 90 degrees, there are no longer any spots on the screen. So if you want to find out what is your maximum order, what is the maximum number of spots that you can find on this screen, then you would plug in theta equal 90, and then you would solve for m. Well, shoot, let's just go ahead and do this right now. So I have a diffraction grating of 12,000 lines per centimeter. So I want to find d. It's going to be 1 over 12,000. 1 over 12,000, that's the number of lines. The number of centimeters, I get 0.00. That's in centimeters, but if I want to convert this to meters, it's going to be 0.000001. I add 2 zeros, so that's my distance in meters. Let's get rid of some of this text here. So that's going to be my value for d. I want to know what is m. D sine theta equals m lambda. Further, I know that theta for my maximum orders is going to be 90 degrees. So I'm going to have, what's this, 1 times 10 to the minus 6 meters. That's d. Sine of 90 equals m times lambda, 436 nanometers, 436 times 10 to the minus 9. That's in meters. Make sure that you know your exponents. Centimeters, nanometers, millimeters are the big ones. Centimeters is 10 to the minus 2, millimeters 10 to the minus 3, and nanometers 10 to the minus 9. Okay, so now sine of 90, of course, is just 1. So if I solve this for m, it's going to be 1 times 10 to the minus 6 divided by 436 times 10 to the minus 9. And I get 2.3. That means that on this screen, I'm going to have my central bright spot. I'll have 2 additional bright spots on either side. But since this goes to 2.3, I only get 2 bright spots on each side. Well, let's say this is asking about how many bright spots are on the screen. So I get 1 bright spot there, 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 and there. So I get 5 bright spots. Okay? That's our diffraction grating, a lot like the double slit, rather. So really the hard thing, if you get the double slit, then the hard thing is getting the not getting confused with the single slit. So you just need to practice that. There's some homework problems to help you with that.